People often don't appreciate, the diverse roles that universities play. So the next two talks are going to talk about different aspects within the academic universe. This first one is from the University of Amsterdam, and I think this is going to be a really cool talk. Leo Huberts, who's finishing up his PhD, is going to be the primary speaker. Ronald, who's been the leader of this group for many years, is also a co-author. He's ready to play chauffeur and answer questions from the back of the room. So, Leo, we're looking forward to your talk. Please take off.
Thank you very much, Jeff. Good afternoon, everyone, or good morning if you're joining from the United States. Yeah, my name is Leo Huberts, and Ronald is also present in the background. And I'm very happy that Martha indicated the importance of case studies already, because we would like to present a case study that we've been doing over the past few years on predicting the success or failure of students, specifically in a high school setting. So this is a bit of the program for our talk. First, a quick introduction. Then I'd like to discuss, of course, the context of the case study, as well as the data that we had available. And then we're going to look at what is the statistical engineering solution that we came up with, and also compare this to what made sense from a machine learning perspective, and how the results compare, and a bit of a discussion at the end. So first things first, this is us. So my name is Leo Huberts. I'm a PhD student, and I'm hoping to defend my thesis somewhere early 2021. I have a background in econometrics, and I'm mostly focusing on statistical and predictive process monitoring in my research. And then Professor Ronald is my supervisor in my research. He's the head of the Department of Operations Management at the Business School with the University of Amsterdam that we are both with. And he will be available for questions or add something if I'm missing anything during the talk, so that's great. Martha already showed a little bit of the framework for statistical engineering projects, which I'm happy with, because this is a little bit of a vague image I see. So it's basically identifying a problem, providing some structure, understanding the context, developing strategy, develop and execute tactics, and identify and deploying a final solution. So these are the steps that also roughly we took during our case study that we're presenting today. It started back in 2015 already, so 5 years ago, with my master thesis, around the time of my master thesis. And it started when I was having a conversation with a high school principal that told me how she was monitoring her students and the probability of failure within a year. And the way that she monitored her students was she had one big Excel file, and she would track all of the changes in the grades every week. If the grades went up, they were green. If the grades went down, they were red. And she would track these grades every week to predict which students would fail or succeed at the end of the year. And well, I was doing my my master's in econometrics, so I was a little bit intrigued by this Excel method, and I thought, okay, I think we can do a better job at this with some statistical engineering methods, basically. So we had a chat about this. She agreed to share their data, and this is a bit of how it started. Now, how it's going at the moment is that a few weeks ago, our research came into early view with the Journal of Quality Technology online. So if you would like to know a little bit more after our talk, then you can go there and check it out. The link is also at the end of the slides. So first, a bit of context on this case study that we did. So navigating a bit of the educational literature first, There were quite some reports in the past 5-6 years that indicate that early warning indicators are very important to the success of schools. So this can be for dropout, but it can also be for individual student success. And we identified that it's quite difficult for a school or even applied statisticians to navigate all of the literature on process monitoring, predictive monitoring, educational data use, to determine basically 3 questions that were important to this school and also to our research. So firstly, what determines student performance? So what should we include in our analysis? And then how can we use statistical process monitoring in monitoring a student progress? So that was one of the options, to use the statistical process monitoring. And then the other option would be to look for predictive monitoring of student results, which we will present in a little bit. Now, the high school that we are talking about here had about 1,000 students at any point in time. It is located in quite a big city in the Netherlands, and there is a single level of education throughout the school. So in the Netherlands, we can have different levels of high school, but within this one school, there was only a single level. It takes 6 years to finish this at this high school. There's a centralized entry test and a centralized exit test, and the ages range from about 12 to 18 years old. Now, there are some exceptions for students that might skip a class or might have to redo one of the years. What kind of data did we have to deal with? So the school handed us this very messy, massive data set from various sources that we had to assemble. And in the end, when we had everything cleaned, we had about 1,700 students in the data and 712,000 individual tests. It spanned a period of 8 years that we had available. There were 36 different subjects like math and geography, etc., divided over 110 teachers. There were some special arrangements where students could have priority to enter the school, because not all the students could enter the school because of a numerus fixus. So a fixed number of students were only allowed. So some of them had this priority arrangement. There were 261 students whose parents were highly educated at the university level or higher. We added some external information like the socioeconomic status of each student by using this countrywide ranking of the postcodes, and we added that to the data set. We had information on learning disabilities, so a lot of kids had some type of attention deficit disorder, and there was a lot of dyslexia also. So there were 326 kids, so that's almost a fifth of the kids that had some type of disability. And this CITO score, which is a score that they do at the primary school level, that is used as a selection tool for high school. So we also had that as a sort of instrumental variable for intelligence, if you will. So that ended up in a whole range of variables, and things like gender, relative age, socioeconomic status, they don't really change during a school year. But there are, of course, also some time-dependent variables that were especially interesting for this monitoring study. So test grades at the start of the year, there are no test grades, and of course they get acquired throughout the year. So at the start of the year at T is 0, we don't have a lot of information except fixed variables or from previous years. But for that year, the grades come in at different points in time. There are also absences, so there are students that are absent from class for various reasons, and they accumulate into this data stream. And at the end of the year at T is 1, we have some end of year grades for a specific course. Now each student takes a set of courses, and they don't have to be the same. So for each student, we have a set of courses that they take, and all of these courses have grades, and each student has some absences. So this varies over time, and all of this information together affects the end of year grades in some way or another. Now, the first question that we had, of course, is, so what, according to the data, but also according to the literature, are important variables when it comes to student performance? So we did an analysis on this, and we found that, for example, disabilities was quite clear from the literature and from our data that it had a negative effect, on the student level, whereas the socioeconomic status, for example, a higher socioeconomic status was related to higher student performance, but it was mostly at the class or at the school level, as we saw in the literature. Language can have both a positive and a negative effect. Now, what I mean by this is that there were a lot of students that did not have the Dutch language as their mother tongue. So they had some other language, and this can have both a positive and a negative effect through something that is called the translator effect. But yeah, so the effect was unclear from the literature, and also in the data, it seemed that it had even a slight positive effect, supporting some of the literature when we looked at the grades for students with a different language. Now, we looked at a few of these variables, and this was quite a high-level analysis, so looking at averages, plotting data, and looking into the literature. Now, another important one was absences, according to literature and according to our data. This had quite a large negative effect on student performance, both on the class level and on the student level. So more absences within a certain class also seem to have a bit of a negative effect on the class performance as a whole. So this determined a little bit of what variables were interesting to us and what should we definitely consider when analyzing the student performance in our case study. So from there, we wanted to see which solutions can we use to monitor their performance and how useful are they as well. So we start, of course, with the statistical solution, and we looked into statistical process monitoring, which is a field that our group has done a lot of work in also outside of this case study. And we will move on to hierarchical predictive monitoring in a bit. But first, a little bit about statistical process monitoring. So it provides techniques to monitor a process in real time, and generally this is done through a control chart. Things like the Huberts or QSUM or EWMA control charts. Most of you will probably have heard some of this before. Now, Weiss et al. In 2016 noted that some large data sets have complex patterns like hierarchical structures, autocorrelation, etc., that could possibly be used in statistical process monitoring. But if we are using a control chart like a Huberts in its basic version, does not really use such a structure yet. But in this data, that's something that is, of course, clearly visible if we think about classes that contain students and each student has some courses that they take. This represents quite a clear example of a hierarchy, and it's a classical example that is also given in the textbooks on multi-level analyses. So, okay, we noted that there is this hierarchy. We note that there's some possibilities there. But first, if we think about just using a simple control chart like a Huberts control chart depicted here on the right, where we take the average grade, we estimate the mean, we estimate the standard deviation, and we monitor the deviation from the mean. So we could do that for grades. But we were thinking about this, and then the question was really, does that work here? And we quite quickly realized it doesn't really work for the solution that we're looking for. And the reason is that firstly, we don't have a clear phase one, right? A student starts the year and there's not a clear in control situation for the student. We could take grades from previous years. These might not be available, or they might be in the first year, or it might be a completely different course. And also what we are actually monitoring then is deviations from their mean grade, which might not tell us that much about how they are going to progress through the year, if they're going to fail or exceed in a certain school year. It doesn't tell us exactly what we are looking for. So what do we need? Well, something like regression control charts might already solve some of our problem. So regression control charts were introduced actually in the very first issue of Journal of Quality Technology by Mendel in 1969. And what regression control charts do is they monitor the residuals of a regression model instead of just monitoring a certain mean of a statistic. Now, in that case, we could calculate the expectation for the grade at steps throughout the year and the actual value, and then consider if that value is very far away from what we would expect, there's something special going on. Maybe the student has a problem, or we don't know exactly, but there's something special going on. So what we are meaning when we have a signal, so when this regression control chart tells us that there is a very large residual compared to what we set out to expect, then that means an incidental anomaly. So it means there's something going on at that specific time, which is interesting, of course, and we also applied that, but it might not answer our question fully, and I'll get back to that in a second. Also, we were considering, should we just do this for the one level, or should we do this for multiple levels? As I noted before, there is some hierarchy in the data. And the question then is, should we not look at this hierarchical model and see if we can do something with regression control charting there? Well, according to J.M.M in 2006, hierarchical modeling is almost always an improvement compared to classical regression. So he would probably advise us to look at this hierarchical option. And that's why we decided to combine such a hierarchical model with using a control chart in what we call hierarchical process monitoring. Now, what does that look like? Well, this is the Bayesian version of a three-level regression. So we have the lowest level is the course level, where we have each grade for a course has a normal distribution with some parameters and some variables and a standard deviation. And the parameters at the course level are allowed to vary on the student level. So that's the second level for J is 1 through N1, which are all the students. But then the parameters at the student level are allowed to vary at the class level. So at each of these levels, we have a distribution for the parameters. And together we can estimate this using the Gibbs Markov chain Monte Carlo method in R, which we did in the end. We have to set some priors as well. I won't go too far into the details, but I just want to make clear. So we distinguish these three levels: the course level, the student level, and the class level. We define a hierarchical structure that looks like this image here at the bottom. So we have classes. Each student belongs to one of these classes, and these students have this variety of courses that they follow. And we will use this structure to model the grade Y as good as we can. So that's a little bit about this three-level model that we applied. So first thing we did was use the three-level and the one-level model for monitoring. And this was when we find signals. So signals can be where the residual at a course level, student level, or class level is a lot larger than we would expect, then such a signal indicates a problem with the student. And it works, of course, both with a 1 level and a 3 level model. So at the 1 level, it indicates some problem with that specific course for a specific student. At the 3 level model, it depends on which level we get a signal, but there is something going on. So there's a value we observe that is so far away from what we would expect, right, that there has to be some kind of issue. But the thing is, these issues are at that moment important for that specific grade, for that specific moment in time. And we had no real way of checking if that signal was correct, because it might be a problem at home, it might be sickness, it might be someone cheated on a test, so they had a grade that was much higher than expected according to our models. And we did not really have a way to check, and it also did not really answer completely the question that we were asking, which is monitoring students such that we can intervene, and monitoring basically the outcome of the student. So are they going to fail in a certain year, or are they going to succeed in a certain year? So that's why we moved to predictive monitoring, where we basically monitor the end of year result. And the way we did this is we defined some event, let's call it E, and a certain threshold. Then we specify our model, in this case the multi-level model. We estimate the parameters, we calculate the probabilities that belong to an event, and then we signal if the probability exceeds the threshold that we set. So in this case, the event will be a student failing the year, for example. Then we can calculate the probability that the student will fail the year at any point in time based on everything we know. And if that probability exceeds threshold C, we get a certain signal. So that's a way of predictive monitoring. And also it allows us to keep updating our parameters to improve the estimations of the end of year probability of failing or succeeding in a certain year. Now, we looked at the predictions at the start of the year, so before any grades were accumulated, and we already noted that the 3-level model performed a lot better. It identifies a lot more structure in the data, which is also visible from the 2 tables down here below. So a 1-level regression would have a very much prediction around a 7 or 6 or 8. So grades are on a 1 through 10 scale. So it predicts anything between 1 and 10. And a 1-level regression would regress to the mean towards around a 7, whereas a 3-level model would identify much more structure and predict also lower grades, higher grades, etc. Now, both the models, if we use them for prediction, they output some distribution for the end of year grade. And that is what we can monitor, of course. We can monitor the distributions for these end of year grades by calculating based on these distributions what's the probability that someone might fail or succeed in a certain year. And this is also what we will do later on. Here we would just like to note that for predictive monitoring, it seems like the 3-level model is the best statistical solution, at least. But then there's also, of course, this new paradigm called machine learning that we had to check out if that might offer us some improved predictive capabilities. And we did some investigations into what we could use, and it seemed like a recurrent neural network was the way to go. And a recurrent neural network is a class of neural networks where the connections between different nodes are a certain directed graph in a temporal sequence. So basically what it means is it can model a sequence very nicely. And of course, we also have a sequence of grades throughout the year. So we wanted to apply this and compare the predictive results to what we had already seen in the statistical solution. Now, some observations that came along immediately were that it was not very easy to implement this, that it's quite unclear still what structure should be used, that there's a lot of software that cannot really handle, at least my laptop cannot really handle the estimation of such a recurrent neural network. In the end, we used Keras to implement. It's a package, and we definitely needed some help from machine learning, computer science colleagues as well to get through this programming. Also, an observation was it's mostly used for machine translation, so that we have sequences of words, and you're trying to predict what a sentence means. Well, this is what it looks like. So a recurrent neural network has some inputs which are in green, which might be previous grades or absences, etc. Then it estimates these hidden states in blue here in the middle, and it outputs, in this case, grades, but it outputs these Ys at different points in time. And one of the things that we ran into is that how do we get an end of year prediction? Because recurrent neural networks are wired to give an output at each point in time. How do we incorporate fixed variables? So how do we incorporate things like gender, the course genre, etc.? How do we input that, because all of the inputs are time dependent? So in the end, we did get this to work, but the solution was not immediately clear. We used padding in the end to get the end of year grade prediction. What that means is that it looks like this image at the bottom here. So what the recurrent neural net does is it takes these green inputs, estimates these blue hidden states, and then in the end outputs one estimate for Y. Now, if some of these green inputs are unknown, then at that point in time, they are set to 0. That's the padding part. And we incorporated fixed variables just as if it was a part of the sequence. So they were incorporated every step in time, even though they were fixed. So we did not get a clear solution to that immediately. But we did manage to estimate recurrent neural nets a few times in a few different ways on this data set and predict end of year grades as well. And of course, it was very interesting to us to see how this compares to the statistical solution, the 3-level model that I showed you a few slides back. So comparing the results, well, here's 2 measures of performance. Firstly, the root mean squared error. Secondly, what we call the nearest neighbors, which is basically the percentage of predictions that are within a boundary of +1, -1 of the actual final grade. So if you look in a table, that would be the nearest neighbors. But in both cases, we have the outputs below here for various methods of estimating these end of year grades. So first things first, we have 5 points in time here. We have the start of the year, that's time point 0, and then we go all the way to time point 0.7, which basically means that 70% of the year is done. We do not include the end of the year because then, of course, all the predictions are perfect. But here we can have a fair comparison of 4 different ways of estimating the end of year grade. Now this Y here is what we would see if we just use the average grade that the individual has for a certain course at that point in time as a prediction. The Y with SR next to it is the simple 1-level regression. So it's simple regression. If we just use a 1-level regression to predict the end of year grade. The Y with an H next to it is the hierarchical models. It's the 3-level model that we saw earlier. And then the YRNN is the recurrent neural net predictions. So looking at this in bold are the best performance in terms of root mean squared error and in terms of nearest neighbors percentages. Now, for the root mean squared error, in every case, the hierarchical model seems to perform best. The recurrent neural net is comparable at the halfway point, but in all other cases, it has a higher root mean squared error. For the nearest neighbors, it's a similar story. The hierarchical model seems to perform best in terms of predictions, and the recurrent neural net is in second place, but it's actually very close to the one-level regression predictive results that we see in terms of performance in these two measures. So this was quite surprising to me, at least, because sometimes when I listen to my colleagues in computer science, it seems that machine learning can do anything and everything. But in this case, it seemed that the statistical solution was a bit better predictively. So we decided to also use that in the actual monitoring phase. So what we did was we predicted the distribution for the grades at every point in time. Well, in this graph below, which look very chaotic, we predict the end of year grades at 15 points in time throughout the year. Now, the distribution of the end of year grades that we predict can be used to calculate the probabilities that a student will fail a certain year. And failing a year at this school was if a student would fail at least 2 of their courses. So 3 or more, then they would definitely fail the year. So you can calculate based on all of these predicted probabilities, what is the probability of passing a year, which is the figure on the bottom left. But the school was also very interested to see the other side of the spectrum, which are students that are expected to perform exceptionally well. So students that get straight A's, to speak in American terms, and get only 9s and 10s, to speak in the terms of this Dutch high school. So they also were very interested in seeing who would have a large probability of excelling, so very high grades. And the reason for this is they would like to challenge these students a bit more to get the most out of their education. So we plotted both on these kind of massive control charts that we see here at the bottom. And then, of course, based on different thresholds that we saw earlier, threshold C, we can calculate the precision and the recall for our monitoring method. So the precision is the number of true positives divided by the total number of what should have been positives, right? So if we think about students that fail the year, the precision is the number of students that we correctly predicted to fail the year divided by the total number of students that we predicted would fail the year. And recall would be that same number of students that we correctly predicted would fail the year divided by all of the students that failed the year. Now, of course, for different values of the threshold C, we also get different values for precision or recall. We have a very low threshold. So if a very small probability already signals that someone might fail a year, for example, then we will get a lot of false negatives. Whereas if we have a higher probability, that would be lower naturally. So these two tables give the precision and recall for monitoring the probability of failing at the top and the probability of excelling at the bottom. So I'll just quickly talk about one situation, for example, at point in time 10% of the year. So this is just after about 1 month from the start of the year. If we take a threshold of 50%, so probabilities of failing higher than 50% would signal, then we would have a precision of 100%, which means all of our positives are true positives. and a recall of 27%. So what that means is that using this method, we would identify 27% of the students that failed a year perfectly at 10% of the time within the year. Also, on the other side of the spectrum, we see similar numbers for predicting the students that will excel. And the precision here at the same threshold level is a little bit lower, but if we take a higher threshold, so if we take a probability of 95% as a threshold, then we predict with a precision of 100% correctly 20% of the students that will also excel at the year. So the threshold C, of course, has to be decided based on context. So if we think back to the steps of statistical engineering, the framework, identifying and deploying the final solution. So the deployment, of course, here it's important to choose a value C that gives you a number of students that you can handle in terms of extra support. And this has to be decided, of course, together with the school based on the data that you have. So this is also something that can be tuned to fit the context of the specific problem. So a bit of a discussion at the end. So the hierarchical model seems to work quite well, and the school was surprised at how well it worked, which was nice. It seems like predictive monitoring is the most useful for the school in this situation, but we can also imagine that there's other situations where the process monitoring version of a control chart, a regression control chart based on the hierarchical model would be very useful. The early warning system can be useful to the high school staff, as was also clear in this example. Now, there might be some techniques that can do better. I talked about machine learning. We looked at recurrent neural nets here. There might be other options that do perform better. And of course, we also very much welcome any suggestions on this. We also think this approach can be applied maybe in other fields. And this is also exactly what we have been working on in the past months, where we are applying a similar method to predicting relapse in people diagnosed with schizophrenia using mental health data in the Netherlands. Now, if you would like to know some more about this case study, it is now online to view. Put the link down here at the Journal of Quality Technology website, and you can find me here. And thank you very much for having me here today. And maybe there are some questions that we can.
Thank you, Leo. That was a wonderful job. We very much appreciate it. Very, very interesting topic here. Do we have questions? Sherry, anything to relay?
Sure. First question that came in is, what was the analysis methodology in determining the dimensions of the student performance?
So I'm assuming that is about the determinants of student performance. So if we think about determining basically the variables that we needed to consider in our analysis as well, what we did was start from the literature, so educational literature, in what seemed to be important for the student performance, and we had to consider if it was available to us and if not. And what we did was we tried to motivate why we could include some of the determinants or variables that are important for student performance, and some could not be included because they were not available. But there are some ways, and this is why the hierarchical model, I think, also works quite well, is there are some heterogeneity, some variance among students that can be included there by having these levels. So there's a little bit more of a flexibility in the way that we model this. If we compare that, for example, to having a one-level model. I'm not 100% sure if that answers the question, but that's the way we went about it. Yeah.
Thank you. And this was also an early question. Following up with that, did you consider supplementing this analysis with the exploratory factor analysis?
We did not yet consider this. No, that might be a good suggestion.
Okay.
Yeah. Thank you.
There was a question about the SPC chart that was shown early on. That it had a unique x-axis that was not time, which would be normal.
Yeah, I can go maybe back to this one.
Yeah, so can you describe what the x-axis is on this?
Yeah, so in this case, the x-axis is the sample number. So this is probably batch data. So we can have, when we're monitoring, in this case, the number of occurrences, we calculate the mean for a subsample here. So the sample number on the horizontal axis, they're all subsamples that are collected. This is just to illustrate what a Shewhart chart looks like. It's not an actual chart that we used in our analysis.
Thank you. There is an observation that that since this work was started in 2015, this is actually kind of before the whole modeling of statistical engineering approach started. So as if it's an example which follows a model by kind of backfitting or retrofitting, then we might want to have the presentation reflect that model and structure it within the statistical engineering structure.
Yeah, that's a good point. So we did indeed, the project itself started, I guess, before also some of these statistical engineering frameworks were made, and it was a bit of a backfitting. But thinking about the structure, it is what we did in a sort of rough way. So it might help to improve the structure also of this presentation by framing it like that. Yep.
All right, I do not see any other questions. Thanks, Leo.
Thank you very much for having me.